Thank you. Yes, I want to talk about hedonic games. As it happens, this was a good day because most of the themes that I want to explore have sort of already been explored, and so I only have to put them back together in a different way.
What a coincidence.
So well scheduled, thank you. So what are hedonic games? A hedonic game is given by a finite set of agents, and what we want to do is we want to put them into groups like this, into a partition. And the agents have preferences over which group they belong to. So this would be an example. So player 1 here, he wouldn't want to be alone with player 3, but if player 2 is there, that's okay. The optimum would be to be just together with player 2. So this is a generalization of stable matching, really, where we also consider larger groups, not just 2 players. And we want to see what happens. So it could be that agents are selfish. Indeed, we're game theorists, so let's assume that they are strategic, and then we want an outcome, a partition like this that is stable. What could stable mean? There are lots of different notions. Here are the single agent stability notions, if you like, which says that to be stable, it can't be the case that some agent would rather switch over to a different coalition in the partition. So coalitions are just sets of agents. Or says, goodbye, I don't like this group, I'd rather be alone. And so partition is Nash stable if no agent wants to switch coalition in the partition.
And there is no rule that they would relate to?
No, not yet. Not yet, not yet. For Nash stability, you can just be, no, sorry?
Size of a group?
Doesn't matter, I can join any group I like, whatever. They have no say. But if you say, well, this isn't really how social interactions work, then you can use individual stability here, which means no agent wants to switch over and is welcomed by his new mates. Right? So here, deviation is allowed if the switching person is strictly better off and all the other people here are weakly better off and allow this deviation to happen. You can define other things, like the people he leaves behind also must agree, but these are sort of the 2 main ones. Then we can do group stability, which is core stability, which we've seen in various guises already. Here this would mean that there is no group of agents that, rather than where they are now, want to form a new table, a new group, and they all strictly prefer that group to where they are. Again, you can have variations where one person has a strict preference and the others have weak preferences, but I won't focus on this here. Right, next problem. So the preferences, hedonic games are large objects, right? Everyone has preference ordering over 2 to the n possible sets, can't do anything with it, so let's restrict preferences so we can represent them. Here's one way to do it, quite a strong restriction, but let's run with it for the moment. Let's assign utilities to agents and not to coalitions. In other words, every agent gives every other agent a number. So I could say, well, you're an 8, you're a 5, you're a -3, not so much. And then a coalition of, I wasn't pointing to anyone particular. So one set is then better than another set if the sum of the numbers, according to me, is better than the sum over here. And any such additively separable hedonic game can be represented by a graph like this, not in general undirected like here, because people might disagree about the numbers they give each other, but just in order to prevent errors, I'm just doing it like this. So this would mean this guy thinks that this is a 10 and this is reciprocated. These 2 don't like each other, and when I haven't drawn an edge, that's a 0. Okay, they are basically indifferent. Good. So now that we have a representation of a hedonic game, let's ask some questions, like, given a game, does it admit a Nash stable outcome? Well, NP-complete to decide. Given a game, does it admit an individually stable outcome? NP-complete. Does it admit a core stable outcome? Sigma 2p-complete. Not so surprising, perhaps, because sort of partitioning problems, they tend to be hard. But so it's computationally a mess. It's not so good. So one idea one might have is, let's replace the summing of numbers with some other aggregation mechanism. Let's take an average, let's take a minimum, let's take a median, or some other way, and maybe this works out. This has been looked at in various papers, but it doesn't really work. So this is a paper from earlier this year, which says that the problem of finding a stable outcome, or just checking whether there is one, is NP hard whenever you allow agents to have relatively rich preferences. Sorry?
What's the difference between average and sum?
Good. And so once agents are allowed to order just these small coalitions however they like, and once they are allowed to have enemies to say, no, with this person I'm not going to form a coalition, if you allow this, then you will have NP-hard problems. And in particular, all this averaging minimum, this satisfies these conditions, and then if you make a large table applying this theorem, you have lots of possible preference representations, lots of possible stability notions, and lots of depression in the middle. So basically, sort of this doesn't really work. So let's try something different in order to get tractability. How about structural tractability? What I mean by that is, let's not restrict what every individual agent may say, but let's say the preferences should interact well. They should be correlated in some way, have some underlying structure. So one first example for this is, well, what I already draw here just actually enforce it, say symmetric additively separable games. My number for you must be your number for me. And this kind of putting things together already works quite well in the sense that these games always admit a Nash stable outcome. You can use a potential function argument, in particular the welfare maximizing outcome is Nash stable. Okay, so this is slightly better. It's not too much better because potential function argument, now finding a Nash stable outcome is PLS complete. That's Gehring and Savani. Finding an individually stable outcome is PLS complete. And if you allow groups to deviate, you haven't gained anything. It's still sigma 2p complete. Right, so let's have more structure around. Let's look at graphical hedonic games, defined analogously to non-cooperative graphical hedonic games. So let's look again at this graph here. Let's forget about the numbers. And remember, there wasn't an edge whenever the number was 0. So now if we look at this, it means that, for example, this guy, he cares about whether this one is in the same coalition as him. He cares whether this one is in the same coalition with him. But he's indifferent whether this person is in the same coalition with him. It just doesn't make any difference to him because it's a 0, and whether you add a 0 or not doesn't have so much effect. So here would be a formal definition. A graphical hedonic game is just a hedonic game plus a graph with the vertices being the agents. So that agents only care whether their neighbors are in their coalition, whether they are together with their neighbors. So formally, some coalition S is better than T exactly if just the neighbors that are in S, neighbors in this graph, are better than the neighbors that are in T.
All the edges that are present have positive weight? Or
not necessarily. So hating is also okay. So this one used to be don't really like you. Yeah. So just if you have any preferences at all about this person, then you need an edge. Now, of course, we can always take G to be the complete graph, and then this condition here doesn't have any bite, but we will want this graph to be small, so to actually give us some information about the structure of this problem. All right, and so how are we going to enforce structure? I tried bounded treewidth, and that happened to work out relatively well, in the sense that deciding whether a graphical hedonic game has a stable outcome can be done, is fixed parameter tractable in linear time actually with respect to the tree width of the underlying graph and the maximum degree of the underlying graph. That is, we can check whether there is a stable outcome in this time, some function of tree width and degree times the number of agents.
If you just only care about the number of neighbors, wouldn't the outcome just be the grand coalition? And then you'd maximize your utility?
Yes. Yes, but this is not in general what you care about. You might also not want certain people to be around.
Okay, because your previous definition, that's what you just said.
Yeah.
You assume bounded degree and bounded treewidth.
Yes, both.
So small degree.
Small tree width. And
Remove degree.
you cannot. Okay, this is bad because usually, this is disappointing because usually just bounding tree width is enough. Here it isn't enough. Intuitively, because the preferences can also in themselves have some more structure hidden away, and so you need to bound that. You can also not drop the tree width and just bound the degree. That doesn't work either. So both of them are necessary. In a sense, you can't drop any one of the conditions. So just quickly, the kind of proof method for this is I define a hedonic games logic, HG logic, which are statements that quantify over partitions, coalitions, and agents. Something like there exists a partition so that for all coalitions they don't want to block. So any sensible solution concept can be formalized, and that you can say things like there exists a Pareto optimal NV-free outcome, things of this sort. And I take this formula, so actually this theorem is more general than I've stated here about stable outcomes. I translate the formula to monadic second order logic, then apply Cosel's theorem, which is a massive sledgehammer meta-algorithmic result which says on bounded treewidth nice things happen. So people who know Cosel's theorem will be worried about this f here, that this explodes. It does explode. The growth is non-elementary. It's bad, 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 but okay, it's linear time in n. Right? So I view this as an existence result of an algorithm saying that on this kind of domain you can do things. And so I didn't really make my fingers dirty, but it's slightly dirtier by looking into dynamic programming, and then you see things like maximizing welfare, for example, can be done in 2 to the kd squared n, which is sort of reasonable. Finding Nash individually stable outcomes can be done in time 2 to the kd to the 5. I'm not claiming that this 5 is optimal, but like this is elementary, right? This is much better than this. So takeaway from this is structural restrictions seem to be a way to achieve tractability in a problem like this, which I'd argue is quite a nice problem to look at. I think it has a nice sort of field and captures things like fair allocation of indivisible objects as well. And if we look at this kind of structural restrictions, there are lots of things that can be explored. So in this graphical Hedonic games framework, you could look at other restrictions on graph topology, like what about the Bipartite case? This is a bit more like matching. And the thing is that all the examples of games that don't have stable outcomes that I'm aware of, they all have odd cycles in them. They all are based on an odd cycle. So I'm not even they might all have stable outcomes, for example. What about height graph, planarity, whatever you come up with? Or are there other interesting methods of having the structural restriction notion, like embedding agents into Euclidean space and then sort of clustering? People want to be central in their coalition, for example, so that they are liked or have more influence in their coalition, something of this sort. You could take inspiration from voting theory and use restrictions there, like single peaked preferences, and have analogs and see whether nice things happen. Or something that we've seen in Edith's previous talk, if you only allow connected coalitions with some underlying social network, then nice things can happen. So I hope that this is a fruitful area of future research. Thank you. So
based on the edges are the same interaction.
the symmetric one, so this slide.
Yeah. Generally we know it doesn't, but in you guys have
Oh. I mean, you can find a stable outcome quickly. That is definitely the case. I don't know whether the actual local search would converge quickly. Is there anything similar on sort of dynamics on bounded treewidth graphs? Anyone?